Hi, my name is Shawn. Today I'd like to talk about how WebCore, Blink and WebKit, how we do compositing in WebKit. So the way Chromium works, we actually have several different pieces that fit together. Blink is is basically our rendering engine. We forked from WebKit recently. And what happens is Blink as a rendering engine uses a compositor. The compositor is implemented in Chromium. What I would like to talk about today is how Blink actually chooses what gets composited, what does compositing really mean, and these sorts of basic concepts. And I will also get into bits of implementation detail and code paths for those who are interested at the end. So yeah, let's get started, and maybe you can go to the slides now. Okay, so what you're seeing here is, imagine maybe this is some sort of HTML page. These boxes could be considered as divs. And the question here is, as we see this animation happening on the yellow div, what actually needs to be re-rendered or repainted? If we assume the traditional rendering model where we have software just going pixel by pixel and figuring out what the color of each pixel is, and we only have one set of pixels to represent the final output image, the answer would be portions of all four layers. Now, yeah, if we're smart enough in WebKit or in Blink, we could say, yes, there's actually only a portion of the actual full-size image that needs to be re-rendered. So I'll look again. Yeah, only this portion needs to be re-rendered, but still, all four layers really do need to be repainted in order to get that scene correct. So what that means is, and by the way, the fourth layer here is the gray background. So what that really means is, as this yellow div, say, as it spins around, for example, it will actually expose parts of the gray element underneath it, and that gray really does need to be repainted just as much as the yellow layer actually needs to be repainted as well. The same would be true for the blue layer underneath the yellow one, and even possibly, unless we're very clever, which we're actually not in Blink, we would also actually have to repaint portions of this red layer on top of the yellow layer. One thing to point out is that computing these pixels, the color of these pixels, actually gets pretty expensive. It's surprisingly complicated. Not only do we have things like background colors, we also have borders. The borders can be curved. We need anti-aliasing for the borders. Then we need to support things like blending for transparency, text rendering, anti-alias text rendering is a whole other beast. All of these things add up, and it becomes quite expensive to figure out what the color of each pixel is to actually render a page. Another example here is, imagine if we have a web page that we want to scroll. Now, I wasn't able to get this to animate or interact on the presentation, but if you just imagine this blue layer here scrolling up and down, what that really means is that we actually have to repaint, re-render every pixel, almost every pixel, on this entire view. And again, that's very expensive. Now you might be asking, well, couldn't we just recognize that this layer is shifting, and instead of re-rendering and recomputing every pixel, maybe we can just shift that pixel up? And that is a very good observation, and in fact, that's exactly what we would use compositing for. And in particular, what we would need is not just one backing store, not just one buffer of pixels, but we would actually need multiple buffers of pixels so that we could store this blue layer in a separate layer, in a separate buffer. And then when we need to, we can just copy it over to the final output image in a shifted position. So that's basically what compositing is. It's the use of multiple backing stores to cache and group chunks of the render tree. So how does this help us? Well, like I just said, it can help us avoid unnecessary repaints. We don't have to figure out what the color of every pixel is every time we need to change something. Instead, we can just cache that and redraw it. It's a little bit of a terminology thing. Repainting in our case would mean that we really have to re-render every pixel and figure out what color it is. Redrawing would be when we already know the color of the pixel and we just need to display it to the screen. So again, repainting would be considered very costly. Redrawing is very cheap. So for example, in this animation that you had seen already, if we had a layer for the yellow that was a separate backing store, if we had a separate backing store for the red layer, these two layers both, so that we could put the red layer on top of the yellow and the yellow on top of everything else, then we would actually not need to repaint anything as that example animates. So other benefits of compositing, it also makes some things practical that otherwise just wouldn't really work, especially if we use hardware accelerated compositing. In particular, things like WebGL or hardware video decoding they're just best done on the GPU. And having to read back from the GPU to be able to render a final output image can get pretty costly and performance would just go out the window. So being able to composite what we render on WebGL or what we decode from hardware video at the same time as compositing both on the GPU it's a great enabler to make things like WebGL and hardware video decoding possible. So what needs to be done when we talk about compositing? It's really just three basic tasks, three straightforward tasks. One, we need to figure out what we would like to put in a separate backing store. And I tend to call these composited layers as opposed to web core rendering layers. We also need to figure out what the contents of those layers will be, render the pixels, and that's what we're calling painting. And we also need to finally draw the composited layers in order to render the final web page. So step 3 is what the compositor's job is, and we actually won't be focusing on how the compositor actually works in Chromium. But for this talk, what I would like to talk about is just a small little micro slice of things where we actually figure out what gets composited and why. And in order to explain things clearly, I will also have to talk a little bit about how things are painted. So in case you're interested in sort of the bigger picture and how things fit together, there's several other talks and links. These slides will be available on dev.chromium.org under the Tech Talk slides link. And these talks and these docs are also available there. So Eric Seidel gave a talk a while ago about web core's guts and how rendering works, even in the software world, with respect to, things like taking the HTML that you provide and converting it from a DOM tree to a rendering tree. That's what Eric's talk is about. Brett Wilson also gave a talk on some other details of how painting works, in particular sort of the APIs used to actually do painting. Chromium's compositor has quite a few docs. This link is one that I think is sort of the overall one, also available on dev.chromium.org. And what I would do in this talk is bridge the gap between once we have a tree of render layers that we can actually render to the screen, how we go from there to a tree of composited layers that the compositor knows how to draw. And it actually is pretty insightful for web developers to have this in mind. Maybe it's not necessarily appropriate to develop your web to tailor to compositing, but it is very appropriate to be aware of these issues when you think about how you want to design your page. So, in order to describe why we would choose things to be composited and how we do that, let's really quickly cover some CSS details. So you might already know about positioning. Elements can be either in what's called normal flow, where layout really does position them automatically, and elements interact with each other when they're all in normal flow. Relative position you can specify on elements. It keeps your elements in a normal flow, but it allows you to position the element with respect to where it would have been in normal flow. Absolute position elements and fixed position elements, on the other hand, actually are taken out of normal flow. So when this layout is computed for normal flow elements, absolute position elements and fixed position elements actually do not affect that part of the layout. And this allows you to actually position with a bit more control your elements. So absolute position elements would be positioned with respect to a containing block. Fixed position elements would typically be positioned with respect to a viewport. So from there, CSS also has this concept of a z-index, which allows you to control the ordering of how elements are layered on top of each other. And this is sort of the beginnings of where compositing becomes interesting, because in order to render things that are stacked on top of each other, and they may be dynamically changing, they may have animations, the z-index is what causes that typically. And so the compositor really relies on z-index a lot of the time. Yes, so one important thing to note is that if we have a positioned element that also has a z-index, according to the CSS spec, that would be defined as a stacking context. So what is a stacking context? A stacking context, it's a very nice concept, actually, and I think it actually gets overlooked quite a lot from web developers' perspective. A stacking context is a way to sort of flatten a group of layers into a single conceptual layer from outside of the subtree. So here's an example where I have 4 different stacking contexts in this example. The fourth smaller stacking context over here is actually a stacking context within the green stacking context. There's no way to indicate that. I'm just telling you that that's what I had intended when making this figure. And you'll see that, okay, so a negative z-index renders below a 0 in z-index value, which renders below a z-index value of 1. And you note that even though I have large z-indexes here in the blue and also in the yellow layers here, these are actually inside of a stacking context, which means that they are flattened to their stacking context before they're rendered with respect to everything else in the DOM tree. So, for example, if we made the z-index 2 on this blue stacking context, it suddenly is designated as the one on top of everything else, and that's what you would see. So the previous example, the z-index was 0. Making it 2 would actually render everything on top. So the way to interpret stacking contexts is they're really flattening the element subtree. So it forms a nice isolation between what's in the subtree of a stacking context and what's outside of the subtree. Inside of the subtree of this stacking context, all layers think that they have their own isolated universe without knowing about anything else. Outside of the stacking context, that stacking context is then just treated like a normal conceptual layer. Atomic, that's the key word, an atomic conceptual layer. So at the end of the day, what CSS spec found, I think, is that this is a very nice place to define the order of how we're supposed to paint things when you give us a web page. And yes, actually, CSS spec does specify paint order. It's a little bit complicated. You can see the full details in section 9.9 and appendix E of the spec. You can just find it on Google. But the basic idea is that first we paint backgrounds and borders for a given element, and then we paint the negative z-index children. Then whatever contents of the layer itself or any other normal flow elements that are part of this layer's subtree get painted. After that, we do absolute positioned and positive z-index children. So what this means is that we're actually creating a tree that is not quite corresponding to the DOM tree. There's cases where you can have an element in the DOM tree that may appear first in the list of children. But if you put the correct z-index on it, it may have to paint last on top of everything else. Another thing would be that depending on how the tree is structured, you may even get what you had as parent-child pairs in the DOM might be more appropriate as siblings when we talk about the order in which they paint. And that's how things are implemented in Blink, where we actually take render layers as the data structure, and instead of using the tree of render layers that coarsely approximates the DOM, instead we actually collect layers into a different tree, and I'll call that the paint order tree in this case. But otherwise, it really is, it implements equivalently the same paint order as the CSS spec. So given that, how do we choose to composite layers? Which layers do we choose to be composited? Well, we would choose composite layers based on when it benefits us or when we really need to. So cases where it benefits us is if we have transparency, maybe we have a transform that is just easier to apply by feeding the transform matrix to the GPU. There may be some filters like blur, reflections, where it's nice to be able to just have that chunk of layers or that subtree of layers cached before we actually reflect it. It's a good opportunity to make it a composited layer so that all we have to do instead of re-rendering it twice is just redraw the same pixels reflected. Scrolling is another example where instead of having to repaint, we can just put everything into a layer and shift the layer and give the wonderful illusion of scrolling. Fixed position elements that need to stay fixed even though things underneath it may change is another example where if we just composite this fixed position element, we don't have to redraw it every time things underneath it change. And then, of course, as I said before, things like WebGL or hardware video decoding are also nice to make composited layers just so that we can take advantage of not having to read them back into software before we actually render them. There's also a necessary evil of having to deal with when we really need to composite. Now, part of this is, I have to admit, how WebCore and Blink are actually implemented, how the compositing is actually implemented. But for the foreseeable future, this is going to be the way things are, and these are realities we have to live with. If there's a layer that overlaps another composited layer, and I'll show an example of this in a second, then we actually have to make that composited as well. Another issue is that if there's some sort of CSS property that needs to be propagated down to composited layers, for example, opacity, or maybe some transform is inherited by an ancestor, those are cases where the parent that has that information needs to be composited just for the sake of having that information in the composited tree as well as in the render tree, so that all the composited layers actually get the information that they need. So overlap, here's an example of overlap. Imagine we have one backing store in our web page. If that's all we had, and this backing store, I'm just representing that by a red rectangle here. If that's all we had, then we would repaint all of these pixels in one backing store and be done with it, no problem. But suppose we thought we would benefit, for some reason, from making this blue layer a separately composited layer. So what we would have is backing store 1 would draw underneath backing store 2. Or actually, it might be more appropriate to say backing store 2, depending on how we talk about things, would actually paint or redraw itself into backing store 1. However, if we do that, the green element that we had intended to be on top would not be on top because we're painting this into backing store 1. This is the case where overlap requires us to create another composited layer so that the green element can actually draw on top of what we thought we would like to composite, which was the blue layer. So it's interesting that this comes up. In the real world, this can cause an explosion of the number of composited layers, which can drain GPU resources quite badly. So this is something to be aware of. In general, personally, I haven't found any explosion of layer counts too badly in the real world, but it's something to be aware of if you're making a very complicated web app, that things that overlap something that might get composited will probably also have to get composited. Okay, so there are some other cases where overlap becomes interesting. Animations in particular is an interesting one, where it's actually not really practical to predict what will overlap an animated layer at any given time. So instead, we just assume that everything on top is going to overlap, even if it doesn't. And I'll actually show an example of that in just a second. So that's another interesting thing to be aware of, is that when you have animations, you might actually see lots of layers suddenly pop up, composited layers pop up on your page, simply because the animation is underneath things. And by bringing the animation on top, you might be able to avoid unnecessarily causing things to be composited in your web page. This third point is also very interesting to note. This is where stacking contexts actually become very useful, because if you have children that are inside of a stacking context, you know that they are treated as atomic with respect to everything else outside of them, outside of that subtree. And what that allows you to do then is, if you made a stacking context out of a subtree of your DOM, you can feel a little more comfortable that you won't have an explosion of composited layers inside of that subtree. Instead, the compositor will recognize, okay, this is a stacking context. I can make one composited layer for this entire stacking context, and I don't need to check if everything else overlaps inside of the subtree, if it overlaps other content. So basically what we do then in Blink is we iterate over this paint order tree recursively, and we ask, does this layer need compositing? Would we benefit from it? And then we also ask, now that we've chosen composite layers for the subtree, once we bubble back up from the recursion, we have to ask, well, is there some reason that maybe we ought to composite this parent as well? For example, overlap, or if something in the subtree became composited that needs some properties like transform or opacity. And at the end, once we've decided if something changes its state, whether a subtree needs to be composited or not composited, we also have to issue that it needs to be repainted. Okay, let's go to some demos, see some examples of this stuff in action. If you'd like to try this on your own, there's probably 4 essential, or maybe these first 3 are the most essential command line flags that you'd like to use. First, force compositing mode, just in case, for example, if you're on Linux, or if you're in a situation where it seems like you might be running software mode instead, force compositing mode will ensure that you're actually using accelerated compositing on all your pages, even if they didn't really require it. So just in case you actually don't see what you expect, try force compositing mode. Show composited layer borders is probably the most useful one. This allows you to, it will just visualize orange and some other color borders around layers that become composited, and it's very insightful. Show paint recs is also very valuable. What this shows is regions of the page and regions of various layers that actually needed to be repainted. That implies that we had to do very expensive paint process to figure out the pixels of that region. And generally what you would like to do to get really performant web apps is minimize the amount of paint recs that you see if you were to visualize this. Another one that we have is not really as useful, but it's still there, is show property changed recs. What you'll see here is these will be layers that, for example, have an animation where, yes, they did not need repainting, but they had some property that changed on them that does require them to be redrawn. If you see these sorts of recs, then chances are you're in a good state, because you didn't need to repaint, but rather you can just quickly redraw them. So, for example, an animation, you might actually see that. So yeah, let's run some demos and see how this looks. So I have a script of my own called run test. This is basically just my way of running Chrome from the command line. I have a command line arc show composite layer borders. Let's see, we can go to poster circle as one of the standard examples for looking at 3D CSS. And what you see here is orange borders. This is the composited layer borders flag showing you that all of these layers here that are being animated in 3D, they are getting composited so that the GPU can do the 3D stuff much faster and much more easily. It also happens, it looks like we have a scroll bar here on the right, even though it's, okay, there it is. Yes, so we have a scroll bar here on the right. This gets separately composited as well because for various reasons, for example, when we scroll, it's easier to have the scroll bar as a separate layer so that we don't have to change any contents of this huge root layer, so to speak, underneath it as we shift that layer up and down. So another interesting thing we can do is let's go to inspector. And what I would like to do is, you can see that basically this text here they're really just simple paragraph elements. There's nothing special about them. And there's this animation going on that is completely unrelated to these paragraphs. However, if I create some layer here with a z index that's positive, and I also need to actually make it stacking context just so that the render tree recognizes it as a separate render layer. So I'll just make it position relative, so I'm not actually changing its position. But what you see now is suddenly this paragraph becomes composited. Why is that? Well, the answer is that because of this animation, we weren't able to assume where this text is with respect to the animation. And so we have to assume that it might overlap the animation, and therefore we create a composited layer out of it. Now in this case, we would judge that this layer is really unnecessary. And the way we could avoid that is change the z-index so that it's actually underneath this animation. So here, when I have a z-index of 1 on that paragraph, it actually is stacked on top of the animation, and we have to assume that it overlaps, so we make it a composited layer. If I made a z-index that was underneath the animation, then there would be no reason to composite it because it does not overlap. In fact, it's underneath the animation. So that's example number 1. Let's see a few other examples. Maps.gl is a fun example. Not only does this show off WebGL, but it also shows off how the compositor is smart enough to render stuff on top of WebGL. So what I have here is using the vector form of Maps.gl. So this map is actually a WebGL canvas on the page. And these elements on top are overlapping a composited WebGL element. And so they also have to get composited. Let's see, any other interesting? Android apps is also a fun example. Here you can see animations in action that actually cause other layers to get created. So what you see here is as I interact, as I mouse over the shadow, the halo around this holes changes. Some of these highlight elements, like the brackets that are focusing on different elements as I mouse over, they animate. And what you see is that depending on what needs to animate, it might actually have a lot of things on top. And those a lot of things on top then also need to become composited because we can't assume that the animation is not actually overlapping. We have to assume that it might overlap. And so this is a pitfall that in this case, it's actually very reasonable. The number of layers is not too bad. The animations are very controlled. the layer explosion disappears after the animations are done, which is generally a good thing. But it's still interesting to note that it can actually accidentally get out of hand if you're not careful in making your web page. It's also interesting to note that we have some 3D layers here that get composited. There's a flip card animation here. If you see the purple composited layer flipping around. The reason that it's purple is because in our compositor, we actually have to create a secondary intermediate thing where we render a bunch of composited layers into another intermediate surface. That's what this purple is. The reason we have to do that is because we have something like this 3D composited layer inside of it. But we're going to want to do something 3D to this outside layer, like a flip card animation. And so what that requires is that we actually have to render a bunch of composited layers down to an intermediate surface, and that's what this blue layer actually is. In our Chromium compositor terminology, we call that a render surface, if you encounter that. Let me go back to the command line here really quickly and show you what it looks like to see paint recs. So here is poster circle again. Now notice that you're not seeing any visualizations on top of the page itself yet. And the reason is because nothing is actually being repainted, and that's a very wonderful thing. That's a great place to be on your web page as often as you can. If I actually select some text though, you can actually see that there's this red visualization that comes up on top showing that, oh, actually this is a region of the page that needed to be repainted at that particular frame. And the reason it's flickering on and off is because the animation is actually going on as well at the same time. And so the next frame is so soon after that the paint rect for the previous frame disappears. That's why it's flickering. If you had a more static page and you selected some text, you would see that visualization stick because no other frame has been rendered after that yet. So that's interesting. Maybe one last thing to show is property changed rects. Again, show paint recs is probably the most important, especially to get performant web apps. You want to avoid paint recs showing up if you use that visualization. But in the case of property changed recs, well, in the case of property changed recs, it's actually a good thing. And so what you're seeing here is that, well, the animations here are actually animating this CSS transform property. And so that property is changing every frame. And these rects it's just a rough visualization to show that here are the layers that actually did need to be redrawn, even though nothing needed to be repainted. That's what this visualization shows. Okay, back to the slides. So I just want to briefly go over some of how Web Core and Blink actually implement the choice of how composited layers work. It turns out there's actually lots of levels of abstraction here just to get different pieces of software plumbed together. So at the bottom of this stack here, we sort of have the output of the Blink side of compositing. The output is a tree of composited layers. CC is the namespace for Chromium's compositor. And so ultimately the output of Blink deciding what to composite is a tree of these CC layer data structures. For each CC layer then, what the compositor will do is it will actually hook back into Blink, asking Blink when it's ready, it will say, Blink, please repaint this composited layer. Blink then has the knowledge of what render layers and render objects and just how to render what's inside of that particular composited layer. So just to bridge the gap between Chromium and Blink, we have several levels of indirection where they are really just essentially wrappers to CC layer. But it's just necessary for the fact that these are two separate pieces of software that are interacting with each other. and they need to talk back and forth, so we have this interface called web layer, and web layer impl is the implementation of that. From there, on the Blink side then, we have graphics layer Chromium is the actual Chromium specific implementation of a graphics layer. And a graphics layer then is this is really Blink's representation of a single individual composited layer. Not all of these will actually draw things. They may exist in the tree just to represent a transform or maybe a clipping region, but the idea is that a tree of graphics layer generally corresponds to a tree of Chromium compositor layers, basically one-to-one. Not quite, but basically. So the real interesting stuff is actually at the top of the stack here, is these top three things. So we have graphics layer as our Blink representation of a composited layer. Then we have this bridge called render layer backing. Render layer backing is the bridge between render layers and graphics layers. So render layers, I'll just assume that this is sort of the input to our problem statement in this talk here. But it actually came from taking the DOM tree, computing a render tree of render objects. That's another class in WebCore namespace, is render objects. These render objects, some of them become promoted to render layers. And so we have sort of a tree of render layers that some of these render layers we will decide to be composited. And those composited render layers will have render layer backings. The render layer backings then will have a small chunk of graphics layers that it puts together to create the entire composited layer tree. So I know that might be a little confusing yet. Here's a visualization to hopefully clears up a bit of it. On the left-hand side, we start with the render layer paint order tree. So the idea would be that here where my mouse is actually maybe the root render view of the page. These other layers are not necessarily composited, but let's say over here, this next red circle is also, we chose to make a composited layer in the paint order. What would happen then is these composited layers would have a reference, or actually they would own a render layer backing, which is represented in these blue circles here. By themselves, the render layer backings are not the final output that we can actually take in the compositor and render. Instead, the render layer backings each manage a small chunk of graphics layers. And I'll show in a second sort of what the purpose of some of these graphics layers are. But basically what happens then is that these render layer backings will stitch together their chunks of graphics layers to create the actual graphics layer tree. So the graphics layer tree that would basically be output to the Chromium compositor is this tree of gray squares that you see here. And so it's interesting to note that from the render layer tree to the graphics layer tree, it's not really a direct correspondence. You can't quite easily say that, oh, this layer on the render layer tree corresponds to this layer in the graphics layer tree. What you have to say is that this chunk of the render layer tree corresponds to this chunk of the graphics layer tree. That's the way to more easily see what's going on here. So inside of render layer backing, there's actually a fairly complicated, hopefully we can simplify this over time, but for now the way it's implemented, it's a fairly complicated set of layers that are used just for convenience, that we can more easily handle things like clipping or containment of a separate background and a foreground. If we found that while we're computing what should be composited, there are some cases where it's actually reasonable to separate the background from the foreground. And so that's what is represented here inside of render layer backing. Clip layers and container layers generally won't draw anything. Instead, their purpose is simply to be a little bit easier to represent something in the tree. So the clip layer would basically clip its entire subtree from the composited layer tree's perspective. And then, of course, once we reach this end game here at the bottom of the chunk of tree here, we would have a container that actually contains the other render layer children as needed. So yeah, I basically just said already why we need so many layers. Well, scroll bars is one I didn't mention. It's always nice to keep scroll bars separate so that you don't have to change the contents of a layer just because you scrolled it. All you have to do is then just repaint the scroll bar as things scroll around. And then, yes, as I said, clips, background, foreground, grouping things together, such as when you have contents that would scroll, you want to group them. Masks, reflections, these are actually implicit. If you look at the code, these are not actually represented as part of this tree, but rather each individual layer might contain a mask, a reference to a mask or a reference to a reflection. Okay, so in terms of code paths, I'm going to go over this quickly. These slides will be available online. It's really something that you just have to read and look through. This is more of a reference than anything that is really worth explaining in a talk. But I will at least quickly say what we have then is we have a paint code path, which Chromium asks Blink to paint. And basically what happens is each graphics layer here has an associated paint phase, with it. And that paint phase is the way that a render layer knows how to paint itself. So when we actually ask Blink, please paint this composited layer using your subtree of render layers, the render layers will then paint based on if they contribute to that particular graphics layer. And the way they recognize whether they contribute is through this phase. So they kind of filter themselves out, and they don't paint themselves to composited layers that they don't actually contribute to. And they recognize, so that it's this phase mechanism that couples that. If you're asking how a render layer paints into a graphics layer, the answer is it uses a phase to recognize which layer it paints into. And then we have the code path which actually computes what actually gets composited. This is the recursive algorithm I mentioned earlier. There's basically two parts to this. One is you want to determine what gets composited, and the second part is you actually need to stitch together these data structures and initialize these data structures. So that second part is rebuild compositing layer tree. And it's worth mentioning, if you do look at this code, when you paint, knowing what you paint into is actually implicitly represented by a context. This graphics context is basically the 2D drawing library that is given to a set of render layers, which was then used to actually draw. So in this 2D library, what's implied underneath is that you already know what is the buffer of pixels that you're going to be painting into. And so all you have to do is use this pointer, use this reference, this context, to actually invoke your 2D drawing commands, and it will draw into the correct buffer. So this is the context that's passed from the compositor to Blink to identify your painting into this correct buffer of pixels. And then, as I mentioned before, it uses the painting phase mechanism for render layers to identify which composited layers it paints into. So these are basically the two pieces of data that need to be passed from the compositor to the render layer in order to paint correctly. Yes, and I think I'll let you all look at these slides on your own afterwards. Let's talk about some of the issues that come up with compositing. Compositing seems like it may solve the world's problems, but it actually doesn't, and it has its own set of problems that gets created. Ideally, what we would like is the compositor to be super intelligent, and it knows what can we composite, what would be the cost of doing so, and what would be the memory cost, the computation cost. what do we gain? And it would be able to optimize between the trade-off of what we gain by compositing, in particular avoiding repainting, versus the cost of actually computing all that stuff in the first place. Realistically, that's a very hard problem, and it's not always clear that there is actually an ideal answer. For various algorithms or various policies or heuristics we choose, we may be trading off making some pages better and other pages worse. So in reality, what we really do is just we composite when we believe that we need it or when we really do need it. For example, 3D transforms are not supported unless you have the accelerated compositor enabled. And once we do that and we accept that it is what it is, whatever we've composited blindly, we just accept that the overhead exists. And we rely on ourselves as architects of this to add heuristics or to identify cases where the overhead can be reduced. But as an algorithm itself, the principle and the fundamental design of the algorithm is basically blind. What are the overheads of compositing? Well, there's the computational cost of actually checking for overlap, iterating over all the render layers, where there can be hundreds, even thousands on some pages. Most of them won't get composited, but they all have to be visited in order to determine whether we might need to composite them. That can get pretty costly. There's the cost of actually managing several more layer tree data structures. We have the composited layer tree structure in Chromium. We have the graphics layer composite layer tree structure in Blink. We have the paint order render layer tree. There's actually a few extra layer trees inside of the compositor, Chromium compositor itself. And mostly, I think the worst issue is that when we choose to create a composited layer out of a render layer, we are saying that we intend to allocate pixels to represent that layer or that group of layers, that subtree. And that greatly increases memory cost for rendering a page. There's also some issues with just rendering in general. In theory, we would be able to in theory, you should not know if we're actually compositing things or not. But realistically, there are some things that you, especially as a web developer, might want to be aware of. Anti-aliasing, we would actually do around the edges of our composited layers, but we wouldn't necessarily be able to anti-alias as nicely the contents inside of a layer. So for example, if you had elements with a border inside of a composited layer, and then you maybe rotated that layer, the edges of the composited layer outside would look smooth because we were able to anti-alias those. But the border on the inside that renders in that layer may not necessarily look smooth because it's actually just pixel data that's rendered into the composited layer. Another issue that comes up is the difference between LCD text anti-aliasing and non-LCD text anti-aliasing, which looks a bit blurrier. Unless we know for sure that the composited layer is completely opaque, we actually cannot. There's just some fundamental limitations that solving them is actually a bit costly, and it's an open problem of how we might eventually solve this. But we actually cannot do LCD text anti-aliasing in that case. The best we can do then is resort to the blurry text anti-aliasing. And for devices that don't have high resolution, this actually switching between these two actually becomes very noticeable and unpleasing. And in many cases, it's not even just the switching between the two that would look like the text is sort of flickering or wiggling a little, but also just the fact that you might get blurry text where you would prefer to have very nicely anti-aliased text. A good example of this is in menus, nav bars at the top that you might make fixed position, for example. If they become composited for some reason, if maybe they overlap some other composited stuff, their text might not be able to get nice LCD text anti-aliasing. In theory, we also want to render at least as fast as software, and generally we do. It is usually quite successful at rendering very fast, but there's often cases where once a page becomes complicated enough, especially if we cannot benefit from avoiding repainting, if we still really need to repaint layers every frame, then compositing actually is not going to be as beneficial. We would have to repaint anyway. We would have to not only do the repainting, whether we were in software or in composited mode, but we would also then, with composited mode, have potentially a larger number of layers that cost more memory, and sometimes the bandwidth of just drawing these layers on a lightweight mobile GPU, for example, can actually become the bottleneck that maybe is just more costly than the painting itself in some rare cases. So I think that's about it. If you have any questions, I'd be happy to take them over the graphics dev at chromium.org discussion list. My LDAP is Shawn Singh, that's spelled ShawnSingh at chromium.org. I'm happy to receive emails as well. And thank you for your time. Thank you for listening. I hope you enjoyed.